topic for today is section 4.5, graphs of sines and cosines. We just got done with 4.2, and I skipped 4.2 because I didn't like it as an introduction to the trig functions, but I do like it as an introduction to the graphs of trig functions. So what we're going to look at here today are just sines and cosines. This lecture will be broken into a bunch of these shorter screencasts as we look at each section of this topic here. So we'll start with just the graph of the sine function. Okay. Now, from the web page, if you click on the link for Pre-Calculus 2, this is the resources you have for this course. I'm going to click here on Live Math Demos, and it pulls up this page that's got a bunch of stuff for pre-calculus, both pre-calc 1 and 2. In particular, I want to look at the unit circle and trig functions. So I click on that, and it pulls up this page here. I'll scroll down so we can look at what I want to look at. In particular, I want to look at this first set of graphs right here. Okay. What we see on the left is the unit circle. This is a circle in black. It is radius 1. And so what we saw from section 4.2, that is if you've got the hypotenuse of 1 there, so the radius is 1, I have the terminal side of an angle drawn in there in black. The initial side, of course, is the positive x-axis. And so the sine of this angle is the opposite over the hypotenuse. The hypotenuse has length 1, so the sine of the angle is just the length of that vertical side. I have it in red. So what I'm going to do here is I'm going to have this length right here. That little red segment is the same length as this red segment. And this red segment will move depending on what this angle is. Now, one thing I want to point out here, I'm going to pull up something else here, is that we have a relationship between angles and central angles and arc length. And that is that the arc length is equal to the radius times the angle. Okay? Well, in this case, the radius is equal to 1. So if I take that relationship and insert it into the first equation, okay, then it tells me that S is equal to theta. So in a circle of radius 1, as we saw in section 4.2, the arc length S is numerically equal to the angle theta. Of course, S is going to be measured in inches, or feet, or angstroms, or whatever. Theta is measured in radians. Okay. So, switching back now to this thing, whatever this angle is, let's say it's 0.7 radians. Well, the arc length from the positive x-axis up to where the terminal ray hits that circle is 0.7. Whatever the angle is, that's what the arc length is. So what I'm going to do is over here, I'm going to slide along the axis, the x-axis here, a distance equal to that arc length, or equal to that angle. They're all the same. So as I click to animate this now, what we'll see is the angle getting bigger and bigger and bigger. And as the angle gets bigger and bigger, this slides further and further over, because the arc length that's being swept out there, which is equal to the angle, is the distance that I'm moving down this axis. The y-coordinate on this graph over here on the right is always equal to the y-coordinate on the unit circle as I'm spinning around. Hence, the y-coordinate over here is the sine of this angle over there. Okay? And what we're looking at is this generation of the graph of y equals sine x. Right? X is being used as the input to the sine, so x is being used as an angle. So the x-coordinate over here is the angle over there. The y-coordinate over here is the sine of the angle, and so I'm using that over there. And you can see the y getting bigger and smaller and positive and negative. Here in the first quadrant, this is always a little weird. Clicking on it seems to go back to the last place you clicked, not the current place. Right here in the first quadrant, you can see that the the y-coordinate is positive. When you get right up to the top, I missed it. Now, anyway, let's see if I can get it this time. Coming around, coming around, coming around. When it comes right up to the top, I click just at the right time. Did I get it? Oh, I did. At that point, the angle's pi over 2. The point right here that the terminal ray crosses the unit circle is the point 0, 1. So the y-coordinate is 1. Sine of that angle is 1. And the graph up at the highest possible value of 1. Okay. Then we move over here into the second quadrant. The y-coordinate is still positive. The sine is still positive, but it's getting smaller. It's going down again. At some point right here, oh, did I get it? No, anyway. When we get over to the second, sorry, to the axis right there, I missed it, there it is. The angle is pi. The y-coordinate is now 0, so we're back down to a sine equaling 0. We then move off into the next quadrant where the y-coordinate is negative. So we're down in the third quadrant. The y-coordinate is negative. You're plotting some negative values here. It gets more and more negative as the angle gets further and further into the third quadrant. By the time you get down to 270 degrees, or in this case 3 pi over 2 radians, you've made it down to a y-coordinate of -1, and the graph right over here is at -1. Then getting into the fourth quadrant, let's click there we go. Getting into the fourth quadrant, the y-coordinate still negative, but coming back closer to 0. You see the graph here on the negative side, but headed back up until you get to 0 when you've made it all the way around the circle. Being all the way around the circle would be 3. No, it wouldn't be. It would be 2 pi radians, or 360 degrees. We should point out that the sine curve would then repeat itself as you went further along this way. I just haven't drawn it that far out, but as the angle keeps increasing beyond 2 pi, the sine would just repeat itself, because you'd be going around this circle again, and you'd be following the same pattern of the y value getting bigger, up to 1, smaller, down to 0, smaller, down to -1, and then bigger, back up to 0 again. It would just keep repeating itself over and over again. We would say that this curve is periodic. It repeats itself. The period of the graph, that is, the period is the distance along the x-axis that it takes the curve to repeat itself. It does one complete cycle and repeats itself from 0 to 2 pi. That distance is 2 pi. I would say that the period of this sine curve is 2 pi. Next, we need to take a look at the graph below, the cosine curve, but I'll do that on the next little screencast. So that concludes the sine.